Good afternoon, everyone. We are the Green Roof team, tasked with the Ohio State University sister case, and we're excited to share our solar and storage designs with you today. But before we continue, we are a cross-university team comprised of students at SIU Carbondale, Case Western Reserve in Ohio, and University of Texas at Dallas. My name is Nelson Fernandez.
Hi, my name is Hank Tenon from Case Western Reserve.
My name is Olivia from SIU Carbondale.
My name is Steven. I'm from SIU Carbondale. We also have two other members who couldn't make it today, Gustavo from the University of Texas at Dallas and Aaron from SIU Carbondale. We also want to give a shout out to our industry advisor, Kyle Smith from Supplied Energy.
So OSU is determined to achieve carbon neutrality by 2050 by reducing their building energy consumption being one of their primary directives. With our integration of solar and storage, we're focused on adding new generation while they are reducing their building energy use, which will in turn be able to increase their resiliency while also reducing their impact on the distribution grid. Next slide, please. So we've been working as an organization for the past 3 years, virtually using tools like Zoom, Discord, ClickUp, Google Drive, to be able to effectively communicate with one another on different engineering designs. Additionally, we're focused on being able to effectively delegate to one another the different components of this proposal. Next slide, please.
So as you can see and mentioned before, the primary challenge area is the Ohio State University Medical Campus, as shown on the left side. And the secondary challenge area is the Waterman Agriculture and Natural Resources area, as shown on the right side of the slide. Next slide, please.
So diving into the development plan, we want to start with the jurisdiction and who's in charge. So all of the roof systems are owned by The Ohio State University. And since OSU is unionized, construction on their sites may need to be performed by their own workers. The Waterman Agriculture and Natural Resource Center is state-owned, so we could actually get contractors out there to do the work. The electrical grid for all of the roof systems is managed by the City of Columbus, with the ag setup being managed by American Electric Power, Ohio. Also, all of the sites are zoned as research park districts that were formed in 1988. In terms of special considerations, there are none except the roof systems fall under the University Area Commission. In terms of permits, we'll need a City of Columbus contractor's license, an electrical contractor's license, and specialized permits for construction within a University College Research Park District. And for codes, we looked at the Residential Code of Ohio, the Columbus City Code, the National Electrical Code, and the International Building Code. And in terms for assumptions for all sites, we assumed that the transformers can handle the load and that all sites have a high leg voltage of 480 volts. And then for a timeline, we have a 6-month plan. So the first 2 months focus on site control. The next 2 months look at permit applications, financing, and then actually engineering the project. And then the last 2 months are power offtake and interconnection.
To start off, our conceptual design for the 9th Avenue West parking garage was considered using carport mounts. They were placed over each. Oh, I apologize, Stephen. I think
This is mine, yes.
That's still yours. I'm sorry.
So the 9th Avenue West parking garage development plan. So for this, we looked at compliance with state regulations, the Ohio Administrative Code 1301. And development also includes compliance with the Ohio State University building design standards found in Division 48.
So as previously mentioned, the design for the parking garage included the carport mounts. And so the solar modules we chose was the SunPower E series 327 watt modules. And we decided to use the IQ8 Plus micro inverters to go along with that. The 497 kilowatt system produced an annual production of 541 kilowatt hours. Since this parking garage doesn't necessarily have consumption data provided, it was assumed that it was going to be exported to the grid. Next slide, please.
So for the safe functioning of our system, there are certain limitations imposed by the IEEE and the American national standard, which includes the thermal and voltage constraints. Voltage constraints depend on the transmission network we are trying to connect our system to, which is for the maximum hosting capacity, and also the internet connection resonance of our system. And the thermal constraints depend on the maximum current the cable can handle before exceeding its temperature rating, and also the hosting capacity. So for the safe functioning of our system, we need to double check if our transmission connections are within the ranges of the hosting capacity, and also to check if the storage systems can accommodate for the energy load. So here in the parking garage, we are connecting our system to the transmission line at the corners of the garage, and we validate our design using the thermal maps provided and also the maximum electricity load of our system that is calculated. Our max system load was calculated to be 520 kilovolt amps after compensating for a 0.95 power factor to compensate for the inefficiency. And the maximum capacity for hosting comes down to about 3,500 kilovolt amp range, which means that our system occupies about 15% of the maximum hosting capacity, means that we are in the green zone. Next slide, please.
And with consideration of the urban area and points of connection, we propose to include electric vehicle chargers into the parking garage, specifically superchargers and DC fast chargers. We found that in the city of Columbus, they have the Smart Columbus initiative, which is backed by AEP, which was mentioned earlier. This initiative began in 2016, focused on ensuring the accessibility of EV education, awareness, and adoption. Currently in the city of Columbus, they have 87 of the total 730 chargers to be free. So we propose that our charger would be free, and then review the financial performance, seeing how it's affecting the financial payback, as well as how many users and customers are using it daily, weekly, monthly, every 3, 6, and 12 months. And we find that financially it's not feasible to continue offering it at no cost, having a cost associated with it, where the university is not getting a payback or revenue, but instead it's paying for operational costs, and then any additional costs would go into a fund that can fund more renewable energy installations, as well as a fund that would go to assisting energy efficiency in buildings based on LEED criteria. So you can overall have that fund go towards more sustainable activities. Next slide, please.
So moving on to the agrivoltaic design for the development plan. So the actual area that we were working with is completely fenced in. So we'll need to remove some of the fence lines so we can get equipment in. We decided that trees should be removed within this area in order to maximize space, and it also helps with carbon offset. The Public Utilities Commission must come out and mark the area and ensure that there are no lines under the building site. And we'll have to bore the creek on the east side that separates the PV system and the AC combiner box and the Carmack Road. And then moving into conceptual design. So as you can see in the image, all of the yellow lines there actually mark off the fence line that we have to work with. So we designed around that, and we also designed for 19 of the trees in the main area to be removed in order to make space for panels as well as underground wiring. Our design uses a SunPower E-Series solar module with a Fronius string inverter. The panels are only on the east side for economic efficiency. We felt that putting more panels on the west side of the lot would cause too many problems with wire gauging and length, as well as just wouldn't be economically efficient. The dimensions for each of these panels is a 3-foot base with a 30-degree tilt towards the south. This will allow plenty of space for sheep to graze underneath, as well as make sure that each panel gets plenty of sunlight.
So once again, the agrivoltaic system is the second side we're connecting to the transmission line. We are connecting to the line at the Carmack Road, which has a maximum hosting capacity of about 3,600 kilovolt amps. And our system load is calculated to be at 2,100 kilovolt amps, which takes up about 59% of the total hosting capacity. So which means that we are also in the clear to implement the system and the connection. Next slide, please.
Now moving on to the rooftop development plan. For our roof systems, all of the roof penetrations have to be flashed. and we must meet fire classifications for IBC 1505.9. For grid tie, all the inverters have to have documents stating complicity with utility requirements, but the PVHC does not need to be reviewed due to connection to the buildings. And we have to make sure that all of the stanchions are properly screwed into the building in order to secure them.
So to give you an overview of the rooftop designs, we chose 3 building locations. The solar modules and the inverters are the same from the parking garage. The modules were based on their durability and efficiency, which is a little bit over 20%. And this will allow flexibility for in case a solar module decides to quit working, it won't affect the entire string. Next slide, please.
For the battery storage, we chose the Enphase IQ Battery 10, which works well with the panels we selected as well. For using the storage side from a controls perspective, we're focused on storing 4 days of autonomy. So if the grid goes out, each building has a full 4 days based on the critical load, which we identified as being the lowest amount of load being received for any hour throughout the entire year of the data being given. Additionally, any additional energy being generated will be exported out to the grid. However, based on the data, we're predicting that will not happen due to the high loads of each of the buildings. As well, we'll ensure that each battery has at least 55% saved up at any given time, unless there is an outage. Next slide, please.
The conceptual design for Dodd Hall, we kept in mind the NEC and international fire codes. We made sure to include the 4-foot walkways as well as a 3-foot eave space. So the 272 kilowatt system will produce annually 316 kilowatt hours. When looking at this, we saw that it had about a 10% energy offset. So next slide, please.
For the for sizing the energy storage, again, we use the 4-day autonomy, and based on the calculations using both the average hourly AC loads and DC generation for a full year, we found we needed 32 batteries in order to have a 4-day autonomy. Next slide, please.
The conceptual design for Campbell Hall, it is an outpatient care facility, and the consumption data was provided so we could have a further analysis for our PV system design. The system is 191 kilowatts, and it has about an annual production of 223 kilowatt hours. When looking at Campbell Hall, it had an energy offset of around 17%, which was the highest of the 3 buildings we designed for. Next slide, please.
For the energy storage, we sized 9 batteries for 4 days of autonomy. Next slide, please.
So the conceptual design for Newton Hall, although it was a smaller location, it was chosen with the intent to have a reasonably high energy offset. It has a 67.4 kilowatt system size, and its annual production is roughly over 71,000 kilowatt hours. This provides an energy offset of about 6%, which is comparatively matches the ratio to that of Dodd Hall, but on a smaller scale. Next slide, please.
For this energy storage, we sized 11 batteries for 4 days of autonomy, and each of the rooftop systems used the same calculation. Next slide, please.
So for the financial analysis, we did use the System Advisor Model, or SAM, software, where we discovered that the cost per watt for the agrivoltaic system is about $1.90, while the urban systems is between $2.45 to $2.75. By using the PPA price of 7.5 cents, the total cost for systems we designed considered to be around $20.3 million. Next slide, please.
So we're a group of students passionate about energy in the team working together. So this has been a great opportunity for us to learn about the technical aspect as well as project management, also to design a system from scratch that's to reach a level of professional and reliable system. And also we believe we have confirmed with our sustainable goals and zero carbon emission standards, and also acts as a great opportunity for us to get our first step into the solar energy industry. And this is the end of our presentation. Thank you for your attention, and we'll be accepting questions.